Okay, and now we move to second part of this session, and we focus more on deep networks, so we already a little bit started. And in particular, we will focus on two different applications. So first is really Toulouse related, so is aerospace engineering. And for this, we have here Michael Bauerheim from SuperAero. He is also part of international chair Hasselt, and he is also quite active in FISIMEI. So he's really an ANITI dedicated member. So please.
So thank you. So as it was said, my name is Michael Bauerheim, so professor at ISAE SuperAero. So today I will show the work we do at ISAE SuperAero in the health share of ANITI and inside FISIMEI on surrogate modeling using some specific architecture, which are known as INR, implicit neural representation, and to go into uncertain quantification, like as it was raised just before, like it's a key when you try to do deep learning, so deep network, how you try to have an estimate of uncertainty from the model and or from the data you have. So the application I do at ISAE SuperAero mostly is what we call CFD. So it means computational fluid dynamics. Basically, it's when you try to solve fluid flows with a solver, so numerically. And so my goal here today will be to just look at surrogate models. So what has been done just before with deep network, we could also address some control problems using deep reinforcement learning that we do also, but it's really with different techniques. So here I will focus mostly on surrogate model. So if you don't know what CFD, we had some examples just before. What I do typically, this kind of CFD, we do what we call high fidelity simulations and trying to have like a detailed flow field of the solution. So here I just try to put together three main applications I have done. So on the left, you have the combustion engine. So you see the flames, which is a turbulent flame. So you have you can see all the small details you have on this kind of phenomenon. And of course, this is what you have in car engines, aircraft engines, helicopter engines, rocket engines, and so on. And your main goal when you try to do CFD is to estimate, for example, pollution, or if you have the good ignition capability, or if the flame is stable, because sometimes it can be unstable and basically can break the whole engine. On the middle, I show you more classical aerodynamic application, which is basically you compute the flow. Here it's over a wing or a blade. So what you have in a rotor of a fan in the engine, or what you have on a wing on an aircraft, for example. And again, you can see like, again, the specificity of the flow is like you see these very small structures inside the flow field, which is turbulence. And here specifically, we're interested in acoustics, for example, but we can also be interested about losses you have in the flow and this kind of stuff. And a third application I do a lot at ISAE SuperAero is bioinspiration. So basically, we try to look at some species. So here it's a boxfish. So it's a fish with remarkable capabilities in terms of maneuvers, efficiency, and so on. So we try to understand them and then to design some robots or drones taking this kind of capability. So if you're able to understand nature, you're able to optimize or to design nicely this kind of devices. So again, like you can see in the wake, so behind the boxfish, you have like this kind of structures. And so what will matter is the size of the object, typically. If you look at the middle, like the size of the wing compared to the size of these very teeny structures. And so this is what this discipline is very difficult. I think like we have difficult challenging because of this multi-scale problem. So this is control, like this is the bottom line, in fact, like since what we was again raised before, like fluid flows, the equation behind, they are strongly nonlinear. And so you have a multi-scale problem. So when you look at the ratio between the large scale, so again like a size of your body, and the small scale, so the small tiny structures, typically like you have an order between 1,000 and even 1 million from time to time in terms of scales. So it's really huge, and you need to capture this with your simulation, and so with your surrogate model after. But this is not just the only challenge we have. It means like to compute the flow I've just shown, it's extremely expensive. It was, again, we had the example just before with Bauerheim. But typically, like the kind of order of magnitude for the high fidelity simulation is roughly 1 million of CPU hours. So it takes a lot of time just for one sample. So of course, you end up with a very few data when you try to do machine learning. So we have a very limited data set. Again, when you have 1,000 of samples, you are rich in my field to do machine learning. And on top of that, so you have limited data set plus each sample, as we have briefly seen, like they are massive. So it's a lot of gigabytes to store. You have many degrees of freedom. Again, between 10 million and even now 1 billion of points inside this flow field. So in each point, you have a value for the pressure, for the velocity, or whatever your quantity of interest. And all those nodes, they are organized in an unstructured format, so typically on a mesh. So we'll say that taking this as an image is not very efficient. So basically, we have to deal with this, with those challenges when we are doing machine learning for fluid mechanics. So I will go quickly on the benefits of deep learning. So before we have seen some presentation looking at Gaussian processes. It turns out like they are extremely efficient, especially on this low dataset regime. So when you have not so much data, that's why like people have used them a lot over the years. And since you have high dimensional spaces, you need to go to this kind of techniques they just propose, like trying to reduce the dimension before doing the Gaussian processes. So when you think about the challenges I've just exposed, basically you say like deep learning is probably not the best choice because like you are very far from this. Like usually you want to have a large data set and so on to make the learning. So we say like, let's try to do that anyway. So try to do deep learning on this kind of problem. So when we have a limited data set, of course, we still want to have a very good accuracy, and especially we are looking at sample efficiency, so how your accuracy evolves when you increase your data set. And what you want at the end is, even with deep learning, can we have a sample efficiency where you are efficient even in the low data region, because this is what you have at the end. Another key topics is how you get some uncertainties, some guarantees, basically how you can trust them. Like even if you have a model, if I give a model to have a surrogate model, for example, for the wing or for the engine, I give that to a company, you need to trust it. It's not just accuracy, like you have something much more that you need to deliver so that basically engineers and so on can actually use them in their work. So this is, my main focus is when we look at all this, AI and especially deep learning here, might not be the best option. So we'll see that at the end we are able to tackle those challenges and to propose some deep learning methods with uncertainties to tackle this CFD applications. So for this talk, I will focus on 2 points. So the first one is how I can represent those complex flows using deep learning, and we will see like how we go from regular convolutional neural network to this INR method and see the benefits of this INR, what we are actually using them. And on the second part, like if we can go like if you are able to represent a flow with INR, so basically if you can predict a flow solution, can you go beyond this and basically try to discover new optimal geometries, for example? And this is where we will introduce active learning. And for that, we will need uncertainties. I will conclude briefly with some research vision, and especially to highlight what we do in the health chair and FICMAI integrative program. So to start with, as I said, one of the challenge of CFD, but you have also here, I put 2 examples on the left about like more solid mechanics, for example. You have also in electromagnetism and other fields like this. You discretize your solution on a mesh, and again, the mesh is very large, low connectivity. And the main problem we have in fluid flows is I try to highlight with this red cross, is like you have a flow over this airflow, like the white body, and you see you have a shock here. And the cross, when you have this discontinuity in the flow, this shock is far from the body. So basically what you end up is like fluid flows is really non-local. You have long distances between the inputs, that would be, for example, the geometry, and the quantity of interest that you have. And we know this is a difficulty when you have deep learning methods to have this long distance relationship. You have the same when you do natural language processes, when you have a sequence and you try to correlate things which are quite far in the sentence. This is exactly the same, but on a mesh. So what people have tried, including me, at the very beginning, so you see like a deep learning for fluid mechanics is really recent. It's, let's say, 2015 for the very first paper where they actually use deep networks. And so they start with convolutional network. So the main difficulty with convolutional network is like you need to make a convolution of a kind of pixel-like format as a structure. So it means like you cannot apply this to a graph structure, so what I've put on the top. So what you need to do is to not adapt the AI for your, like you try to adapt your AI to your solution. So basically you just take your graph, your field, you just interpolate on a regular Cartesian grid, and then you have a kind of an image, and then you can do a convolution. The problem with that is like, so of course it's small, like you have rate sharing, it's easy to train. The problem is like you have a lot of interpolation losses. We've seen like we have like multi-scale problems. So as soon as you will interpolate on this grid, you will have difficulty to manage these small scales. It's really not resolution invariant, and this is a huge problem for us. So basically, if you change your interpolation, you change the grid, the CNN doesn't work anyway, or very badly. And CNNs, they are really local. This is what I try to to highlight with this red square, which is the kernel that you try to translate over your image, and you can see it's really local. Of course, you can try to make something more global with kind of unique architecture and so on, but you need to build something on top of that to have this kind of long-distance relationship. People try to move beyond this and say, but if you have, since you have a graph, a mesh, just try to put deep learnings that are specialized for graph. And these are graph networks, and you have plenty of different versions of graph networks. And basically, it works like on each node, you make an aggregation when you take the neighboring nodes, and you make an aggregation on the yellow node, the one you try to predict. I'm not going into the details of graph networks, but again, like what you gain is, of course, those methods, they are adapted to the mesh or to the graph structures that you have, so this is a good point. But again, it's very hard to make them non-invariant when you change the resolution. So basically, you change the resolution of the graph of the exact same case, and your graph network doesn't work anymore, or you need to spend a lot of work to make it work. It's really non-local in space. So again, like you have difficulty with graph network to have long-distance relationship, and it's really memory expensive. So again, it doesn't seem to be the best solution. And so quite recently, people said, okay, let's try to do something much simpler and treat the field as a continuous field now, and not a discretized one. Like we have discretization because we are using CFD, and so you need to discretize the solution on a mesh. Deep learning, you can do something different, and so you can really look at this continuous field. And so people say, okay, just use let's say the simplest network possible, so MLP, multi-layer perceptron. And what you do is just you pick the coordinate, X, Y, or Z if you are 3D, the time if you want. You have your network parameterized by the weight, so here W, and you just output at this point the quantity of interest, so the velocity at this field, the pressure at this field, and so on. So a very simple idea. Of course, the problem when you do that is you are able to learn one solution. And what you want, of course, is to learn a family of solutions when I will change the operating condition of the machine, when I will change the geometry, and so on. And so you need to do something. And basically, like what people have tried for a very long time is like to put these parameters as the input of this main network. And basically, when you do that, it doesn't work, or it doesn't work very nicely. So the tricks, there are two tricks to make MLP working to have a family of solutions, especially for CFD problems. Basically, the two tricks are like this. The first one is in yellow, so it's between your coordinate system and the main network with the parameters W. You use what we call Fourier features. Basically, it's like you lift your coordinate system in a kind of a random Fourier basis. I put the pictures on the top. When you can look at when you have on the top is when you do nothing. The bottom is when you add this kind of Fourier features, and you can see that again you get this kind of multi-scale, like better resolution. Basically you help the network to learn the high frequency content of your image, and so for us it will be for the flow. So this is the first trick that you need to make. And the second one is instead of putting, so here operating position, I put alpha, which is the angle of the flow, and m, the Mach number, or the word geometry. Instead of putting them inside the input of the main network, you create another network, phi. And so this operating point and geometry, there will be input of this phi network, an hyper network. And this hyper network, what it does, it modulates the weight of your main network. So basically, the Wi, now they are a function of this hyper network. So basically, the hyper network, it modulates the weight of the main network. And it works really nicely. So basically, you learn a solution, and when you have a kind of conditioning that just change slightly your main network, so your main solution, to adapt to your new operating condition or new geometry. And this is what we do, and I will try to show you an example to convince you that actually this works very nicely. Of course, the benefits we have is now it's resolution invariance, because it's a continuous way to look at the solution. So you have not discretization behind it, so it's completely resolution invariant. It's non-local in space because everything is inside this main network. This is what we call implicit neural representation. The whole representation of the solution is in the main network W. It's really memory efficient. At the end, you have very small networks. It's a very small MLPs with just 3-4 layers is sufficient, and the same for the hyper network. It's quite easy and flexible to train, at least for the experience we had when we trained from one case to another. It's really versatile, since it's point-wise, for example, compared to what was shown. Like if you have some data at some localized point with a probe or something, you can try, or you could, because we didn't try so far, do kind of data simulation techniques on this kind of stuff. Yet it's not fully mature, so there is still a lot of research to push forward these INR methods. So in terms of application, I pick one among the many we have done. Try to have something representative of an industrial case. So here you can see it's a turbo machinery, Degen 380 that we have at Isaïe Super-Héros. And we will concentrate mostly on the fan. So this is a rotating part that you see when you look at an aircraft, like the first rotating blades that you see is a fan. And so we have created two data sets. One, which is specifically for one geometry, the Degen, and for which we have multiple operating points. And another one when we have various geometries. So basically, we make a lot of different geometries based on known turbo machineries to have a data set. And this data set, to make it realistic, we keep to a low data regime, because this is what I want to show. And so typically when you have one geometry, multiple operating position, we have 60 samples only. And when we have multiple geometries, we end up with something around 300. So this is the number of samples, and each sample here, it's a 3D flow field with roughly 10 million of nodes inside. The good thing with INR is since it's point-wise, during training you can subsample the points, so you don't have to put all points, so the 10 million of points, and try to do a learning. This is what you have to do if you do CNN or graph network. So here, for example, we try to subsample, and what we show, this is the graph. So on the bottom you have this ratio, so how many nodes you skip. So this is a ratio between 1 and we try to have something around like 1,000 or even 10,000 as a ratio. So you really don't use a lot of points. And then on blue, you have the training time of the network, and in red, you have the accuracy of the model. And basically, you can see that when you go from 1 to 100 as a ratio, the MSE, so the accuracy is quite flat. So basically, you are not losing anything to subsamples. And you get, instead of training on 10 million of nodes, you have 10 millions divided by 100 here. In terms of training time, you have a huge gain, because typically you can see like for this 100 ratio, you have something around an hour and a half. So this is for the case when we have one geometry, multiple operating points. If I want to summarize this, so for one geometry, we end up with roughly 1 hour of training with 60 samples. When you have multiple geometries, 300 samples, you end up with 8 hours. So this is really a training time on one GPU card that you can have in an industry almost in the day as soon as you have these samples available. If we want to go a little bit deeper about this MSE, it doesn't mean a lot like this. So if I try to look at the flow fields, I will maybe be quick on this. So I look around the blade at 3 cuts so that it's easier to look at the flow fields. And here you have on these plots, you have all the data sets. So we have the 300 simulations with various geometries. And the strange part is like when we do the design of experiments, you end up with this kind of clusters, like you have this kind of 3 clusters, which is usually what you don't want to have when you do DOE. But for the exercise, it's good because I can pick the green dot here in this plane, and it's kind of out of distribution. It's not inside the training data set. So I will show you that point to see if actually the network is able to learn something. And this is the solution. So on 2 planes, yellow, like the red is on the mid plane of the blade, and on the right, the blue is really at the top. On the top ones, you have the CFD solution. On the middle, you have the INR solution. And below, you have the error. Basically, what we show is that you have a very good representation of these complex flows with a lot of physics. So I have not the time to show everything, but typically we have shocks. Here you can see on the right, like the blue part is in fact a huge vortex that go around the blade tip. And this is where you have the losses in the thermal machinery. So this is the one you try to get to design your blades. So basically, when you give that to someone in turbo machinery design, they are quite happy, and they start discussing with you to how you can take this INR for optimization, for example, to have an optimal blade. Is it working? Okay. So let's say I have fast and accurate prediction on realistic flow, and of course there are like new methods trying to push forward those methods. I want to quickly jump to this discovery part. Now that we have some predictions, let's try if we can actually discover really something new, so something out of data set. So I take a completely different examples. It's a flapping motion. So we try to optimize this kinematic of a wing, and this is what you try to do when you have a very small drones where you cannot design rotors or something like this. And so we make basically simulations of these flapping wings that you make random, just to have a data set. You learn from the kinematics to some metrics, so efficiency, loading, etc. And when you have this model, you make an optimization to optimize the kinematics. And this is what we have. So this is a pipeline on the bottom. And the graph, maybe it's a bit slow, is the 2 metrics. So it's a multi-objective optimization. On the below axis, you have how much lift, so how much loading you can take with this drone. And on the vertical axis is the efficiency. So let's say one is strength and the other one is efficiency. All the small crosses, they are the data set, so the random one. And you have the Pareto front that goes along. And when you pick simulation along this Pareto front and you recompute the CFD, basically you end up with a triangle. So you see, basically you are making some errors on this Pareto front. And so the technique is just like you do active learning, so you reuse this data set you put this point into your dataset, you retrain, and you get a new step like this. So basically, you are just having 7 more samples in your dataset, but the Pareto front now is much more converged. So typically, it's like the dots, the red dots, they are closer to the triangles, which are your true data. You can do another steps and so on, and basically it converges quite rapidly. And so here, like the active learning was guided by errors. And what we show, especially on the right part of the plot, on the CL, so on the high lift, is that we are able to actually discover something new, because like when the CL max is 1.4, whereas on the training dataset, we are around 0.9. So a huge gain in doing this active subspace and being able to explore something new. And when we look at those kinematics, basically this one was quite intuitive to get. It's like if you swim in a swimming pool, you want to be efficient. So this is the most efficient kinematics. You make large movement quite slowly. But if you want to escape, for example, for something, you will do a very different kinematics, and this what were less intuitive to get, but this active learning approach was able to find it. Basically, you do something quicker with low amplitude, and you try to do. So this is nice to see that we're able to find this kinematics here. The point is here we only guide with the error. So of course we could guide with other things: uncertainties, curiosity, surprise, novelty, whatever metric you want. So here I will briefly finish with uncertainties. So it was talking about deep ensemble just before. Basically, like when you try to put uncertainties for deep models, the easiest way, like instead of doing one model, you do just multiple of one. And you train n models, and from these n models you compute n solution, and then you make the variance of them, and it gives you a notion of uncertainty. This is of course costly, so what you can try to do is Monte Carlo dropout. So this is extreme on the other side. So you take one model. With dropout, you try to make some new models, but that are really correlated from the first one, but still you are able to compute variance, and this gives you a metric of uncertainty. And what you try to do is to do something else, because basically, like, so deep ensemble is very good but costly. Monte Carlo is not so good but cheap. So we try to do something behind, based on a collaboration with EPFL and Pascal Fua, on the zigzag methodology. Basically what you do is like you just change slightly your architecture and you feed back your output as an input, which is quite simple. You can do that for almost all networks you have. And the idea is basically you try to rethink about your own answer. So if I give you a question, you answer and say, are you sure, typically? So I give you back are you sure this color is blue? If you say, yes, it's blue, okay, you are confident. If you change, no, maybe it's red, then you have some doubt. This is exactly what we try to do here by thinking on your own output, and basically we'll construct a measure of uncertainty based on the difference between 2 successive paths of this iterative process. And so basically, like, the good thing is we're able to prove mathematically that it works. So we have the demonstration that the difference between the 2 outputs is a measure of the total uncertainty of the problem. And plus, if you have access to some repeated experiment, you can even separate epistemic and aleatoric part. So if you have questions, I will go back on this, but I will try to move quickly. So we tried this zigzag approach on these 2 test cases, the noise produced by a drone with a rotor, and aerodynamics on this airflow. And the solutions are here. So basically, we look at the OROC metric. When you have 1, it means it's really good. So you can see that deep ensemble, of course, is really good, but it's costly. Anti-dropout, not so much, not really robust, but it's cheaper. And zigzag is really in the middle, quite robust, depending on the dataset we train, but again, quite cheap. So this is what you try to achieve. And of course, the next step is to guide active learning that I showed before with this kind of uncertainty measure, especially in INR-like architecture for fluid flows. So to conclude, AI in CFD is still new, and we still need a further improvement on the methodology, especially to go toward like full aircraft, multi-component problems and so on. So there are still a lot of things to do. This is what we try to achieve in the health chair with Alena. Typically here, like the goal is to improve guarantees, not just with uncertainties, but with hybridization, so to put AI into the simulator itself. And inside the integrative program, FISIM AI, led by Paul Novello, where we try to create an open source toolbox with this kind of INR and other techniques to benchmark those methods on data set, develop hybrid methods, develop uncertainties, and do that all those with kind of benchmark on realistic scenarios for CFD, but it could be on other fields. If you have, we are always happy to have this kind of benchmarks on large engineering problems. Thank you very much for your attention. If we have time, I can take a question.
Okay, so many thanks for this great talk. Do we have some questions? Okay, we have to pick randomly because time is flying.
Thank you, Michael, for the presentation. A question about explainability. So there is a usage of techniques, deep learning included, also to make some appropriate representation, and then maybe some simpler models, maybe to do the propagation, let's say, or the. Does it create questions about explainability to really understand what is going on, or the knowledge of physics helps you? Contrary to other applications of deep learning?
No, explainability is still a question we try to solve. It's not trivial, of course. But yeah, it's crucial because most of the time when you have optimal kinematics, optimal geometry, you want to understand why. Typically, it's not just there is an end up of the optimization. So we are trying to look at some techniques, indeed, like also to look at kind of symbolic or neurosymbolic approaches, so also to put some symbolic approaches into that. What works, let's say, the easiest way, in fact, is to do the explainability part with regular physics-based post-processing. For example, for this kind of optimal kinematics, we develop from the physics, so there is no network there. Post-processing to see typically like why this kinematic is efficient and to track like the CL or the efficiency inside the flow. So force partitioning methods for people that know that, for example. So this is the easiest way, but we are really working on the other side, like interoperability of the network itself. I think it's a true challenge now.
Okay, perfect. I know there are many questions, but maybe you can catch Michael after the session because we are a bit late. So in between, we can set up Simone.